In this lesson, we're looking at combinations including restrictions. So the focus of this lesson is about being able to identify scenarios where we have restrictions and then working out how we can calculate the total number of selections including those restrictions. So the first one, when we look at the inclusion of a specific element, is focused around the scenario where a specific element has to be included in the outcome in the selection. Okay, so in this scenario, obviously that's going to reduce the total number of selections, and it will create something like a 1C1 multiplied by n take 1 C R take 1, in the sense that we're selecting this one value out of a set of 1 itself, and then the total number that we have to make the remaining selections from is reduced by 1, as well as the total number of selections that can be made. Right? And that would work the same if it was an unknown. So if it wasn't just a single, we could have x guaranteed selections. Then we'd have something along the lines of xcx multiplied by n take x C R take x. So that should make relative sense, and we can make a really simple example here using this. So for example, we have 4 people and we're selecting a group of 3, but 1 must be included. And so that means that 1 must be included, and then there's 2 spots left for the remaining 3. So that would be that the number of selections is 1C1 multiplied by 3C2. And so that would be 1 multiplied by 3. And so there's 3 ways that selection could occur. All right, so nice and easy. That's our first one. The second one is when we're looking at combinations of multiple groups. And this is when we're saying that we're selecting A from our first group and B from our second group. And we end up with the number of selections then being a combination of both of them. Now, because we're selecting from group 1 and group 2, it's going to be a product. So we'll have N1CA multiplied by N2CB. So it's as straightforward as that. And so a really simple example again would be, so we have 10 males and 8 females up for selection to a board. If 2 of each must be selected, how many possible boards are there? And we can see that that's pretty straightforward. So what we're doing is we're selecting 2 from 10 males and then 2 from 8 females. So the end is what gives it away here. We've got 10C2 and multiplied by 8C2. So the total number of sections is a product between these two. So that would be 10C2, which is 45, and 8C2, which is 28. And 45 by 28 is 1,260 different boards that could exist from those original members to select from. Okay, so I'm hoping those 2 applications make relative sense. The last one we have is combined permutations and combinations. And so this generally occurs when we have a scenario where we have to choose from multiple groups and then work out how many different ways we can arrange them. Okay, so you can see this is a really simple example. We're saying that we're looking to determine the total number of arrangements, so that's important, of 5 people, where 2 are selected from a group of 5 and the remaining 3 are selected from a group of 4. So the number of arrangements is what we're looking for, but before we can arrange, we need to have this number of selections. So this will mean that what we're looking for is the number of selections multiplied by 5 factorial. We're multiplying by 5 factorial because after we select those 5 people, we have to work out how many different ways we can arrange them. So for the selections, we've got 2 selected from 5. So we've got 5C2. We have 3 selected from 4, so 4C3. Then we're multiplying by 5 factorial. So that means we have 5C2 multiplied by 4C3 and then multiplied by 5 factorial. And so we end up with 4,800 different ways that we could arrange those 5 people selected. Okay, so now we can see those individual restriction approaches. We'll look at a few examples. So the first example Grace belongs to a group of 8 workers. So we've got 8 workers. How many ways can a team of 4 workers be selected if Grace must be on the team? So this is a selection where we have a specified inclusion. So the number of selections will be 1C1, and that's Grace. And we're multiplying by, there's 7 people left for 3 positions, so 7C3. So that means we've got 1 multiplied by 7C3, which is 35. So that means there's 35 possible ways that Grace can be on the team. When we look at B, we have a hand of cards consists of 5 cards drawn from a deck of 52 playing cards. How many hands contain both the Queen and the King of Hearts? So in this case, we start off with N is equal to 52 and R is equal to 5, but we're reducing by 2. So we're starting off by going that number of selection is we must have 2, so 2C2, and that means we're left with 50, and we're choosing 3 of them. So that is 1 multiplied by 50C3, which is 19,600, and so there's 19,600 different ways that we could get a hand that contains both the King and the Queen of Hearts. Alright, so pretty straightforward as long as you break it into those 2 parts. The next example, we've got 4 students to be chosen from a group of 8 students. So 4 to be chosen from a group of 8. 2 members of the group, Sam and Tess, do not get along and cannot be on the team. So how many ways can the team be selected? So we have this restriction here where they cannot both be on the team. So that means that we're selecting one of those 2, and then we're selecting the rest of the members from the remaining. So the number of selections will be, we've got 2 and we're selecting 1, and that means we've got 6 remaining to select 3. Now I did forget something. There's an or here, right? Because we could have one of the 2 in the team, or we could have neither of them. So that means that we would have 2C0, which is just going to be equal to 1. And that means we've got 6 for the remaining 4 spots. So that means we've got 2C1 multiplied by 6C3 plus 2C0 multiplied by 6C4. So it was a little bit more complex. We had to think about that. So that's 2 multiplied by 20 and 1 multiplied by 15. So we have 40 plus 15, which is 55 different possibilities. Okay, so it would have been pretty easy to forget this, or not realize that it's even a possibility. So when you get asked a question like this, make sure that you do fully consider. So the consideration here was that the team doesn't have to include Sam and Tess, so we could have one of them and then the remaining members, or we could have neither. Okay, so we'll move on to the next question. So we have from 7 women and 4 men in a workplace, how many groups of 5 can be chosen if, first of all, there's no restriction, so that's pretty straightforward. The number of selection is 11, and we're selecting a group of 5, so that would be 11C5. So there's 462 possible selections that can occur. We look at B, containing 3 women and 2 men. So this, in this case, we've got 3 women and 2 men. Now there's 7 women that we're choosing from, so we're choosing 3 from 7, and there's 4 men. So that means we have 7C3 multiplied by 4C2, which is 35 multiplied by 6, and that's 210 possibilities. When we look at C, we've got this containing at least 1 man. Okay, so this is where it's going to be a little bit complex, because at least 1 man means we can have 1 man or 2 men or 3 men or 4 men. We can't go past 4 men because there is only 4. So that means our number of selections are, we could have, first of all, 1 man. And if we have 1 man, we have to select 4 women. So we'd have 7C4 multiplied by 4C1. Or we can have 2 men, which means we would have 3 women. So we'd have 4C2 for the 2 men. Or We can have 3 men, which means we would have 2 women, so we'd have 7C2 multiplied by 4C3. Or the last one is that we could have all 4 men, so that means we would have 1 woman, 7C1 multiplied by 4C4. Okay, so to calculate this out, we have 35 by 4 and 35 by 6 and 21 by 4 and then 7 by 1. And so this adds up to be 441 different possible selections. And finally, we've got containing at most 1 man. So to work out at most 1 man, then we can have 0 men or 1 man. So that means we would have from 7 females, we would have 5. And then we would have 0 men, or 7 females, we select 4 and 1 man. So that will be 21 times 1 and 35 times 4. So 21 plus 140 is 161 possibilities. Okay, so we'll move on to the next example. In this one, we're asking in A, how many arrangements of the letters in the word duplicate can be made that have 2 vowels and 3 consonants? So this one is, we're trying to rearrange them, but we're also selecting 2 vowels and 3 consonants. So the number of selections will be, let's see, so the number of vowels is 4 and the number of consonants is 5. So what we're saying is 4C2 and 5C3, and then we're rearranging them because there's 5 selected. So we're multiplying by 5 factorial. And so that will be 7,200 different arrangements. And look at B. Now this first one I should have said it was arrangements because we were selecting and arranging. For part B, the number of arrangements. So we've got a president, a vice president, a secretary, and a treasurer. We're chosen from a group containing 7 women and 6 men. How many ways can this be done if exactly 2 women are chosen? Okay, so the easy way to think about this is we're choosing 2 women. So that means we've got 7C2, and that means we're choosing 2 men, so we've got 6C2. Now the tricky part about what remains is, because we're choosing 4 of them, we've got 2 women and 2 men, and it's not defined which positions they can fall into. We have to look at all the different ways that we can arrange these 4 selected individuals. So that means that we have to multiply by 4 factorial. And so that works out pretty easy to calculate. 7C2 multiplied by 6C2 and then multiplied by 4 factorial. And we get 7,560 different groups that can be chosen. Okay, so that concludes the lesson. We can see that these can get pretty complex, and as the questions get harder and more is involved, then you have to think a little bit more about what you're going to do. We can see here with a couple of these, particularly this last question was hard to interpret, and obviously these questions here, C and D, where you had to look at a combination of different groups. Okay, hope that all makes sense. Thank you for listening.